Myself, Dr. M. Vijaya Shankari, Assistant Professor, Haji Kartara Uttar Haudiya College, Uttamapalayam. Today in my presentation, I take topology. First we say the topology definition. A set capital X be a non-empty set. Here tau be the collection of subsets of capital X. We call tau is called a topology on X if tau satisfies these three conditions. First condition is empty set and the whole set are belongs to tau. Second condition is the union of elements of subcollection of tau is in tau. That is union of all open sets is in tau. This is the second condition. Third one is the intersection of closed sets of elements of tau is in tau. When tau satisfies these three conditions, then tau is called the topology of capital X. We call the set capital X together with tau is a topological space and is denoted by x comma tau. The subset capital A of capital X is an open set of capital X. Capital A belongs to tau. Capital X be the whole set, capital A be the subset. Capital A belongs to tau. So we can say that a topological space together with its subsets are all open such that capital X and empty are both open and closed, and also infinite union and finite intersection of open sets is also open. Next we see some example for a topological set. Let a capital X equal to set of all ABC and consider the collection tau equal to set of all X empty singleton set A comma set B comma C. We said that tau is the topology since tau contains X and empty. Then the union of a subcollection of tau belongs to tau. Third condition, the intersection of a finite subcollection of tau belongs to tau. Therefore, these three conditions are satisfied. Hence, tau is the topology on capital X. Tau satisfies the topological three conditions, so we said tau is a topology. Next, we see the theorem. Let capital A be a subset of a topological space capital X. Here X be the topological space, capital A be the subset. Then the closure of A is the union of A and its derived set, that is A bar. A bar is the closure of A equal to A union A dash. A dash be the derived set. We prove the theorem. Let small x belongs to A bar. Then x belongs to each closed superset of capital A. The element small x belongs to A bar. A bar be the closure of the subset A. The element x, small x belongs to the closure of the subset A. Then small x belongs to each closed superset of capital A, say capital F. Small x belongs to A bar and small x belongs to capital F. Also, we know that A is the subset of A bar. It is a known condition. A is the subset of A bar. A bar be the closed set. A be the subset. The set A bar be the closure of A. Therefore, A is the subset of A bar. If small x belongs to capital A, then small x belongs to A union A dash. Here x belongs to A. The element x belongs to A bar. The element x belongs to capital F. Here x belongs to capital A. Then x belongs to A union A dash. Since x belongs to A and x belongs to A dash. If x does not belongs to capital A, then we are show that X belongs to A dash. For this, suppose that X does not belongs to A dash. Then there exists an open set G containing small x such that G difference a singleton set X intersection A is equal to empty. That is G intersection A equal to empty. The open set G and the subset A, there are no common element, that is G intersection A equal to empty, which implies capital A is the subset of G complement, then capital F is a closed superset of A, and then X does not belongs to capital F. This is contradiction to the fact X belongs to A bar. Therefore, X belongs to A dash. Hence, X belongs to A union A dash. So, A bar is the subset of A union A dash. Next, let small x belongs to A union A dash, then X belongs to A or X belongs to A dash. Clearly, X belongs to A bar since A is the subset of A bar. If X does not belongs to A, then X belongs to A bar. So we are show that X belongs to A bar. That is, X belongs to each closed subset of capital A. Assume that there is a closed superset capital F of capital A such that X does not belongs to F. Then X belongs to F complement which is equal to G, an open set. Since X belongs to A dash, that is X is a limit point of capital A. Since so G intersection A equal to empty, which implies F complement intersection A is not equal to empty, which is contradiction to the fact that A is the subset of F. So we conclude that A union A dash is the subset of A bar. Combining equation number 1 and equation number 2, we get A bar equal to A union A dash. Hence the theorem is proved. Next, we define the basis definition. When an element is a basis of capital A, it satisfies two conditions. First one is a base for a topology tau on X is the class B1 of open subsets of X such that every element of tau is the union of members of B1. First condition is tau is a base for a topology tau on X is the class B1 of open subsets of X such that every element of tau is the union of members of B1. Second condition is let capital X be any set. A basis for a topology tau on X is the class B2 of open subsets of X such that for every small x belongs to capital X, there is at least one element B2, say B1, for which X belongs to B1. Second condition, B1, B2 be the basis element. There exists B3 and basis element. Then small x belongs to B3 such that B3 is the subset of B1 intersection B2. These two conditions are satisfied, then X be the basis element of B1. This is the example for basis. Let capital X be the topological space. There are four elements A, B, C, D be a topological space and consider the class script B. Script B be the collection of basis elements equal to set of all X, empty, singleton set B, singleton set D, singleton set B, comma C, comma C, hello, sorry, set of all A, comma B. The basis element B generate the topology. Therefore, the basis elements are all open sets of subsets of X show that script B form a base for a topology. Script be the collection of a basis element. It generate the topology. Here, this example, we show that script B for a basis for a topology. Solution: script B equal to x empty singleton set B singleton set D set of all B comma C set of all A comma B the class of subsets of capital X, the set. Now taking the union of members of script B, we get tau be the topology. Therefore, the basis element generate the topology. Tau equal to x comma empty singleton set B singleton set D, then their union. These two singleton set union is B comma D, then the set B comma C, the set A comma B, their union A comma B comma D, B comma C comma D, comma set of all A comma B comma C. Therefore, we union the basis elements. This generates the topology which is clearly defines topology on X generated by the class script B and is called a topology. Next definition, subbase definition. Let x comma tau be a topological space, a class S of open subsets of X, that is, S is the subset of tau, is called a subbase for tau on X if and only if finite intersection of members of S form a base for tau. Then S is called a subbase for tau. This is the definition of the subbase for the topology. Then there is an example for a subspace. Every open interval A comma B in the real line R is the intersection of two infinite open interval A comma infinity and open interval minus infinity comma B. Open interval A comma B equal to open interval A comma infinity intersection open interval minus infinity comma B. But the open intervals form a base for the usual topology on script R. Hence, class capital S of all infinite open intervals form a subbase. Then the theorem for continuous functions. A function f from x tends to y is continuous if and only if the inverse image of every closed subset of y is closed in x. It is a definition. Here, if and only if condition is given, therefore we find, therefore we prove this theorem by necessary and sufficient condition. Prove. Suppose we take f from x tends to y is continuous, then we prove the inverse image y is closed in capital X. We use the definition. Let capital Y is the subset of Y be closed set. Capital Y be a closed set. Then F complement equal to Y minus F. Closed set complement is open. Since F is continuous, F inverse of F complement equal to F inverse of Y difference F equal to F inverse of Y minus F inverse of F. But F inverse of Y equal to X, so F inverse of F complement equal to X minus F inverse of F is open in X, which implies that F inverse of F is closed. Conversely, we assume that every closed image of every closed subset of Y is closed in X. We prove F is continuous. Here we take a capital G be an open set is the subset of Y, then G complement is closed. F inverse of Y minus G equal to X minus F inverse of G. That is x minus f inverse of g is closed in x, f inverse of g is closed in x, then hence its inverse image is closed in X. G be an open set in Y. Its inverse image F inverse of G is closed in X. Therefore, the function F is continuous. It satisfies the continuous definition. Next theorem. If capital A be the class of topology tau on X generated by A is the intersection of all topologies on X which contains capital A script A. Here tau dash equal to intersection of tau I and A is the subset of tau dash. We wish to prove that tau equal to tau dash. Here tau is the topology containing script A, and tau dash is the intersection of all such topologies. Therefore, tau dash is the subset of tau. Now, suppose capital G belongs to tau. By the definition of topology, we have G equal to union of set of all AI1 intersection AI2 intersection and so on AIN such that AIK belongs to script A. But A is the subset of tau dash, which implies script A is the subset of tau dash, but script A is the subset of tau dash, which implies AIK belongs to A is the subset of tau dash. AIK belongs to tau dash, therefore its intersection belongs to tau dash, which implies G equal to union of all finite intersection belongs to tau dash. From equation number 12 and 13, we combining tau is the subset of tau dash. Therefore, we combining the equation 11 and 14, tau equal to tau dash. The topologies are same. Thank you.